All right, good. Okay, we're going to talk about voltage dividers. Okay. Sometimes we have power supplies that are not the correct voltage for the circuit we're working with. So let's just talk about a circuit. We have not used it yet. Mark has, but the rest of you haven't. A circuit with a resistor and a lead in it. Okay? We're going to talk about LEDs a little more when we get to diodes, but we're just going to use them for now. So I'm just going to talk a little bit about them now. Okay, everybody here has used a LED, right? Steve, you used one. Casey, no problem. Mark, I know you've used them. So, okay, so it's an LED. An LED is 2.7 volts. If I have a 9-volt battery, I have to do something to make sure it doesn't burn up. In other words, whatever 9 minus 2.7 is, R1 has to drop that voltage or the lead goes away, right? Okay.
You buffer that even more?
You can use a bigger resistor.
Well, I'm just asking, you calculate right on the line, or do you calculate a certain percentage?
Yeah, you can calculate it right on the line, but you have to know a little bit more about the lead. So use a data sheet for the lead, and then you know enough about the lead so that, and it might say 20 milliamps, or it might, whatever it says, then you know the lead completely. You know the current in the circuit. Because if the lead is in the circuit in series, even though it's an active device, it still acts just like a resistor, and the little rule we have holds true. It's the rule. The current in the circuit is all the same through all the components. Okay? So leads, that's true. Now, can you measure the resistance of a lead? No. Ain't gonna work. Okay? But you can calculate it because you have a voltage and a current, so you can calculate it. 170 ohms or whatever that comes out to. Okay? All right. So that's good for one lead with a resistor, but I may want multiple voltages out of my supply. Okay? And I can do this with just one voltage if I want, but I may want multiple voltages. So I may build myself what's called a voltage divider. Now, a voltage divider is simply a device. It's actually a network of resistors that allows me to pick off certain voltages off of my supply. Now, the actual resistors make up a resistor network, a series resistor network in this case, and at certain points, which we already know that because we've finished doing some of that, I will have certain voltages. If I said this was 10 volts, then I know that this side right here is 0 volts, and I know that this is 10 volts. So I pick resistors that my supply will not end up burning up because there's a certain current limit to my supply, and my resistors are a certain size so that current is not exceeded. I would like to find resistors that will be added up and come out to whatever the current of the supply is, maybe a little less. At this point, I will have voltages at these 2 points here, and they will be voltages, we don't know what they are yet, that I can use. Now, if I have a circuit that draws a certain amount of current, and that's all it ever draws, it's consistent, another resistor, and it never changes, then I can attach it with reference to ground. I can attach my black box, which would be a resistor in this case, okay? And it will draw a certain amount of current at a certain voltage, and this divider will be able to provide that, okay? Now, what's it going to look like here? Well, it's going to look parallel to that resistor, isn't it? So I'm going to have to make sure I pick resistors that will allow this. Now, if this is way bigger in resistance, let's say it's like 2 megohm. It's so much bigger than this resistor, it's really not going to, we're not going to really care. So it's a voltage-driven device. You guys talked about voltage and current-driven devices, right? Okay. So this is a voltage-driven device. So this voltage here will drive this black box here. It's in parallel, but it's so much bigger than this resistor here that it's not a big deal. So this voltage will stay proper for this voltage-driven device, black box. If this is a small resistance, say the same or somewhere around the same, we immediately have to take into account that they're in parallel, and the current is going to change through both resistors. When the current changes, that means R3 is going to change. That presents a problem for a lot of circuits because they're current-driven. If they're current-driven, voltage dividers have a problem. What is it? They change. We want this voltage right here to stay the same if we can. So this works really well for large resistances. If I put a motor on here, I got a problem. One thing, motor's variable anyway, but even that's a heavy load, okay? All right, so, but let's just talk about the voltage divider to start with, okay? We're not going to talk about any loads on it. I just wanted you to notice that, okay? There's going to be a device that comes later that takes care of that problem. It can vary the current and keep the voltage the same, okay? All right, well, 10 volts. Let's take a look at some resistances that we could put on there. If I told you that all of the resistors are quarter watt, I have now determined my resistances, haven't I? If they're all, what if I told you they were all three the same and they're quarter watt? Okay, now I've determined what my resistors can be, right? Because what does it really look like? Well, if this is RT, okay, and I said there the power is 1/4 watt, okay, which is 0.25, right? Ah, darn it. Okay. Okay, so, all right. These actually look like RT, so I could actually redraw this as RT 10 volts, and I told you that it was, RT was 1/4 watt, 0.25 watts. So what does that tell me now? Well, I know that P equals what? I times E?
Yeah.
Okay. So, I know that P is 0.25, and that equals I times 10. So I equals 0.025 amps, right? So now I know the current through all three of these resistors. I also know the wattage. So now I know the voltage on all of those resistors and the resistance, don't I? How do I do it? Okay, so let's do it. Current through these resistors is what? 0.025. Okay, We know the voltage across all three. Do we have enough to get it? Let's see. IRE. We don't, do we? Because we don't know the voltage across. Oh, I told you one other thing, didn't I? What did I tell you? All three resistors are the same, didn't I? Okay, so now I know that what's the total resistance? Well, RT is, well, I have current and what do I got? Voltage. RT, R equals E over I. E over I is 10. Can we get it this way? 0.025. What's that come out to? 400 ohms. Okay. And divide that by 3. 133.3 ohms. So each of these resistors 133.3 ohms, because I told you they were all the same, didn't I? Yep. Okay, so now what we can do is we can find the voltage at each of these points, can't we? Okay, because we know the resistance for each resistor and we know the current. So we go, okay, let's see, for R3, let's do it right over here. E R3 equals what? What do we got? We've got the current and the resistance equals I times R, right? Equals I times R, 0.025 times 133.3. What's come out? 3.3 volts. And that's true for each of these. Now, we're rounding, so it's not going to be quite right. Okay. So I know at this point my voltage is 3. Let's do this. Come on. Yeah. Okay, I know at this point right here my voltage is 3.3 volts. What's my voltage right up here? Well, it's 3.3 plus 3.3. So this voltage right here is going to be 6.6 volts, right? And it's going to be 10. We're going to say, well, it'd be 9.9, right? Be 10 volts, okay? Because we rounded. All right? So now I can draw 10 volts, 6.6, or 3.3. And as long as I don't draw a lot of current, I'm okay. What happens if I start drawing some current? Then it looks parallel and it changes the resistor in the voltage divider. So what would I use these maybe for? Well, I might use these as just a bias voltage to hold something up that didn't draw any current or very, very, very little. So I just need a voltage to place it at 3.3 or 6.6. I can make my voltage divider any voltages, and I can even add more. If you look in the book, you will see on page, get to the voltage dividers here. Okay, if you look on page 97, you'll actually see a voltage divider that they in figure 1 or 8-13 that they actually put together, and it looks like our voltage divider. Okay. Now, if you look at figure 8-14, they have a pot, don't they? Notice the pot's in the center. It's not all the way up, not all the way down. It actually produces a voltage divider by using a pot. Kind of fools you. It's not two resistors, but when it's in the middle, say 100K, That's 50K on each side. So that makes a 2 resistor voltage divider. So that would be a variable output voltage divider. Again, so that we can bias something or something that doesn't draw a lot of current. We can use it on it, okay? Now, if you go on to the next page, you will see voltage dividers 8-16. Well, 8-15 has 3 resistors, and then notice that they have a resistor off to the side on the bottom. Again, that's a small resistance. Let's see, it's 1K and 10K. So that 10K will affect that 1K, and it'll look parallel. The 1 milliamp will want to split between the two. It's not a bias circuit, it's actually a load circuit. So you have to take that into account. When you calculate the current in the circuit, you're going to see, well, they have a 1K and a 10K. You're going to see a tenth of the current through the 10K. Okay? So it's going to split up. That 1 milliamp is going to be 1 milliamp. A tenth of it is going to go through the 10K. The rest of it's going to go through the 1K. The upper resistors, they're just voltage dividers, but nothing's happening with those. They look like a limit resistor of a single resistor in series if you look at the total. So you have to be really careful. One will affect the other. What if it was like 100 or a million or a 10 million ohm resistor, a 10 mega ohm resistor? Well, now it's bias. Is there a little current? Yeah, a little tiny bit, but it's pretty negligible. So then a voltage divider works really well to bias that circuit. Okay. All right, and they even do. Notice that they do a 4 resistor in 8-16, and they actually do the calculations, I see, and they show the current. Now, if you're going to use a voltage divider and you're going to drive a black box circuit and you know the resistance and voltage for that black box circuit, then you can tell what the current's going to be out of that black box circuit. Then you design your voltage divider to give you the proper voltage by placing that in. You say, okay, I got a parallel resistor, so I know what size resistor here will give me the proper voltage so I get current through the black box to make it operate, okay? When I pull that off, what happens over here? That voltage is going to change right away, isn't it? Because I'm going to unload the circuit. That little parallel circuit goes away, and it's just a series, or just a single resistor in the series circuit, right? Okay, so you got to take that into account. You know, I always remember that's what I did, okay? All right. We're going to build one of those here in a minute, but I want you to go to page 102. We have something special. By the way, this stuff has to be in your notes, so you should put this in your notes, okay? We're going to talk about something called a Wheatstone's bridge. And we use this particular idea to be able to determine something about a resistor or about, or if we're making measurements or whatever, okay? It's a balanced circuit. We put a voltmeter in the center. When we change one of the resistors, we either get current flow one direction or the other. The meter is going to have a zero position. It can go negative or positive. And you can see in the picture, we put the voltmeter right in the center. So what's going to happen is we're going to see current flowing in one direction or the other direction. We're actually going to draw it up here, and we're going to look at it once you get this in your notes, okay? We're going to draw this up here. We're going to do we're going to go ahead and do a voltage divider, and then we're going to turn around and do a Wheatstone's bridge on our boards, and we're going to do some measurements so you can kind of see how it works, okay? So let's get this in your notes. And I apologize. I should be telling you when you need to put it in your notes, and I forget sometimes. Okay, we're going to shut